It's my great pleasure to introduce Dumitru Erhan, who is a staff research scientist as well as tech lead manager in the Google Brain team in San Francisco. He received his PhD from the University of Montreal in 2011 with Yoshua Bengio, where he worked on understanding deep networks. Later, he has done research at the intersection of computer vision and deep learning, and he has many great papers, influential. For instance, in object detection, it is single shot detectors, SSD. For object recognition, GoogleNet, and the inception architecture. For image captioning, he has a nice paper on show and tell. There is visual question answering, unsupervised domain adaptation, active perception, and many other great works. His recent work has focused on video prediction and generation, as well as its applicability to model-based reinforcement learning. He aims to build and understand agents that can learn as much as possible to self-supervise interaction with the environment, with applications to the fields of robotics and self-driving cars. And today he's gonna be telling us about enabling world models via unsupervised representation learning of environments. So Dumitru, the floor is yours.
All right, thank you for the introduction. So this is being recorded right now? Is that?
Yes.
Okay, excellent. All right, so thanks again for the invitation. And yeah, so my name is Dumitru, and I'll be presenting sort of not one single paper or anything like that. It's a set of ideas, a set of results, and some sort of research agenda that kind of unifies these things into one, maybe coherent thread. And this is a bunch of work that we've done over the last 2-3 years ago, and from then until now. Some of the stuff we just put on archive, like literally a couple of weeks ago. And I will send these slides later. So if you're trying to make notes of what papers I'm talking about, there should be links in the slides. Right. So I'm going to talk about world models, and we'll see what that is if you don't know what that is yet. And let's see. So yeah, what I'm going to start with is I'm going to say is that, of course, we all know there's been very major progress in machine learning and computer vision, especially in the last decade or so, right? A lot of it has been fueled by deep nets, but that's not the only reason that we've had so much progress, I'd say. And we know that there's a lot of stuff that works for some suitable definition of working. We have things like image classification that works really well, lots of object detection successes. We've essentially conquered things like Go, which is very impressive. There's this paper that I think people, whatever used to be Uber research or Uber AI, that I just saw the other day that does superhuman on all this every single Atari game. There's many successes of machine learning that that were maybe not as predictable to us 10 years ago. And one of the hypotheses as to that I have for why all these successes are there is because we've become accustomed to all these very big data sets. A lot of the successes are in scenarios where we have lots of well-labeled data sets, maybe practically infinite labeled data sets like Go. You can generate as much data as you want, and it's perfectly labeled, perfectly curated in some sort of sense. There's no noise, et cetera, et cetera. We have these very high capacity models that can do very good function approximation, these deep neural networks. And we've had some sort of amazing progress in compute. Things like GPUs and TPUs and all sorts of other kind of, custom hardware, basically. GPUs didn't start as hardware for deep neural networks. They just turned out to be like that. But certainly NVIDIA has made them better and better at neural networks over the time. So this combination of like lots of good data, very powerful models that can do lots of fancy kind of approximation of various input to output functions, and very fast compute. Well, I'm not saying that that's success is guaranteed in that sense, but to some extent, it's maybe not unexpected. Now, what I was going to argue is that what we really want is maybe agents that can work in, or models that can work in situations that are different than this, right? That are where we don't necessarily have a lot of well-curated, well-labeled data sets, right? We want intelligent agents that can learn from little data, and that can adapt to new settings and new scenarios. Maybe we have a new goal or new objects that they need to handle, or new categories, or whatever. Maybe they need to learn a new game, and they need to do it quickly from few examples, from few labels. If we're ever sort of hoping to have like some sort of a robot deployed in people's homes, we can't expect people to like spend an eternity labeling all the objects in their home, where they are and what they are, such that the robot can like find them, or if the robot is there to help them do something, achieve a task that the person is not able to do. Right. So there's plenty of such scenarios where, you know, just thinking about like someone labeling the objects in the scene may just be you know, too expensive or just impractical. Now, the premise of what I'm going to be talking about is that we can do a bit of a sort of a bootstrap a bunch of these objects, a bunch of these agents, by sort of making them learn how the world works. And what does that mean? And it's making the agents imagine the effects of their own actions. And, you know, this kind of works both ways. If you can sort of make the agents imagine the effects of their own actions, they can learn how the world works, right? So it's sort of bidirectional relationship in here. And it's a bit vague. I will go into sort of concretely what we mean by that. But how would you learn how the world works? It's sort of an interesting question. What does that mean? We'll try to use generative models. So this is this talk. It's not just generative models. It's kind of predictive models. There's another way that's popular, but I'm not an expert. I have not done anything, I think, as far as I know, any work in the topic of meta learning. But that's another way of sort of learning how the world works. Is instead of trying to formulate, you know, an input-output relationship and try to learn it, you sort of try to understand from a sequence of problems how to solve problems. That would be meta learning, and then try to quickly adapt to solving a new problem from the experience of you having solved other problems. But I'm not going to cover this in this talk because it's a different kind of approach. Now, what's a world model, right? So, sounds a bit fancy, but I promise you, I did not come up with this name. And it's just a shortcut for saying that we want to learn a model of the world around us, or the world, or the environment around the agent, from observations. So the agent is observing something and is trying to understand how will this change in some reaction to what the agent is doing. We want to do something useful with it. So in put in different words, we want to do representation learning of environments. Now, again, I will sort of be a bit more concrete as to what examples of useful things are there. We may want to learn reinforcement learning policies from very few rewards. Again, coming back to my sort of example of a household robot. We don't want sort of someone in the, you know, with a home robot, you know, spending like, you know, I don't know how many years would be to like say, to give, you know, a bunch of rewards to a robot, 1 million rewards, so that they learn a task of fetching, you know, a glass of water, right? That would just be like an impractical thing. But a lot of the sort of state-of-the-art RL policies or RL agents, that's what they would require. We would want these policies to generalize to new tasks or new domains or new objects or new households or new instances of objects quickly, right? We would like to sort of enable agents to do one-shot or zero-shot learning of behavior. What that means is that we would like, even without sort of demonstrating the behavior, we'd like the agents to understand just from a description of something what they can do. Ideally, we would like agents to learn something in a simulated version. Like that's a lot practical for, especially for robotics. Lots of time in robotics, we cannot kind of necessarily collect interactions with the real world, but we have some simulation of the real world. And we would like to quickly adapt a policy that was learned in those simulations to the real robot. You may think that this is sort of hard. And sometimes, the way I say here, from collected interactions. So it's basically, think of it as a robot watching YouTube videos of something being done and trying to sort of learn a policy of how to do that. And we as humans are able to do that to some extent, right? I've certainly during the pandemic, I watched a lot of YouTube videos on how to fix things in the house, and I learned a few things. Of course, I'm trivializing things to some extent. I have some background knowledge of how to do things in life. And I think one of the underappreciated things about models of the world is that they add an ability to debug agents. And that's important in a lot of the practical kind of applications of this. The most important one that I can come up with is something like a self-driving car, where it's good to understand, to pose kind of counterfactual questions about what would have happened had the agent done this rather than the action that it did take, right? You can basically sort of simulate what the environment would look like in reaction to different things happening in the environment. I will say that the premise and this hypothesis of basically what I'm describing as model-based reinforcement learning is not new at all, right? So there's plenty of sort of, this is a field maybe as old as I am, maybe even older. And there's a variety of classical control algorithms for robotics that are in fact model-based approaches. But the key difference there is that they operate on ground truth states. And what I mean is that they sort of assume that everything that is important about the environment is given as input to the model. And I don't mean that everything is given. It's just that only the important things and only that, right? And with high precision. So like the joints and torques and all that stuff of the robot arm is an input, right? And nothing else is the input, right? So the only thing that you need to model there is the dynamics. How will those ground truth states move in reaction to an action from the agent? And that's fine if you're operating some sort of a robot arm in a factory or something of that type, right? Where there's nothing that you need to generalize to. The world is the same all the time. So in a world model kind of scenario, we don't make this assumption. Basically, we need to learn what's important from observing the world, right? So the agent observes the world via some pixels. Doesn't have to be pixels. We just assume it's because it's easier for us. But some representation of the environment that's not just the ground truth. The agent then interacts with the world by doing some actions or some torques or whatever. It observes the consequences of its actions. And then optionally, it receives the reward, right? Maybe delayed, maybe sparse, and maybe not at all. And the premise of this whole body of work is that we can learn a lot about the world by just predicting the future, right? We can just observe and try to predict what will happen. Then we observe what happened, try to predict again, and so on. The question is how to do it, right? So this sounds, to me, sounds sensible, but doesn't mean that we can actually do that. If you've ever heard Yann LeCun talk recently, if you don't know him, he's a famous machine learning scientist. He calls this kind of predictive learning or self-supervised learning. And supposedly, I'm not a neuroscientist, so I don't want to make big claims, but I think he makes this claim that humans and animals do this, that they sort of try to predict the effect of their own actions when deciding what actions to take. Maybe I don't do this prediction for every single action that I take, but certainly when the action has an important consequence, I try to think a bit harder. So we kind of, maybe we try to visualize it in our head before acting, right? Now, what if we had a way to do that directly? So we observe the present, call it a state, a sequence of frames. We observe the action that the agent takes, move the arm to coordinate XYZ, and then we observe the future state once the action completes. We could learn to model that sort of directly tries to infer ST+1 from ST and AT. And, you know, if you're a machine learning person, you know, sort of like, yeah, sure, formulate this as a supervised sort of learning problem. It will work eventually. And yes, it will work eventually. But in general, this is hard. The state can be a video, and that's pretty high dimensional. And despite all of our sort of progress in hardware and deep nets, actually working with videos is pretty hard. The action space can be continuous and multidimensional. There could be multiple agents operating on that environment. You may not even know what is happening to the environment, who does the action. And that basically makes your future non-deterministic. Maybe not in a sort of some sort of philosophical, you know, is the future deterministic ever? But from a partial observability kind of, you know, point of view, because you do not observe every single thing that's happening just from those pixels, there's many things about the scene, about the environment that make it inherently unpredictable what's going to happen. So a lot of what we've done is try to solve this problem of predicting the future state from the current state and the actions with these generative and predictive models. And I'll go sort of deeper into them in the next few slides, but I'll sort of start with this example, basically of, you know, a lot of our papers are basically of using this kind of data set of where we're given a couple of frames of a robot arm interacting with some objects, right? And typically we're starting with a couple of frames, truly just one or two of them. And maybe we're also giving as input what actions in terms of like coordinates of the arm is taking. And we're trying to predict what the future will be, right? Maybe we can also give what actions the arm is going to take. So we just want to predict where, you know, how the scene will look like and where the objects will be. And that's basically the problem of video prediction, right? You're sort of trying to predict the future directly. And that's kind of hard in general. There's a lot of challenges. Just sort of to summarize the big challenges is that there's a lot of uncertainty into the future, right? Or how to handle uncertainty, how to handle this partial visibility. Generating actually believable predictions, like if you show them to a human side by side with real videos and ask them, you know, which one looks more real, is pretty hard. And the longer into the future, you don't even have to go that long into the future, but long horizon predictions are very difficult. Most of these models, they just completely degenerate into something that's obviously bad after, like, I don't know, 20 frames or so, right? So that's not even a second, generally speaking. And I put a bunch of papers in there in the sort of part of the links. And if you go through the slides, you can go through them. But a couple of years ago, maybe even now, this sort of state of the art that I'm putting in there, that's about as far as we can get in terms of good video prediction. We can get maybe 10, 15 believable 64 by 64 frames in a contrived setting, right? So not like take a YouTube video randomly and predict what it's going to look like. That's just not working. I'm not sure it will ever work in the next like decade. But like if you have a data set of like robot arm interacting with objects and you have big enough data set, you can get to like a couple of seconds of prediction that looks believable. And maybe we can do 128 by 128 now, even though it's going to be pretty slow. And again, I'll sort of come back to this a couple of times, but the big problem is stochasticity, right? There's just multiple different plausible options into the future. And the reason, even in this contrived setting of an arm and object, is that we don't know many things about, there's occlusions, there's that simply make it impossible for us to reason what will actually happen with the objects. We don't know the masses of those objects, the coefficients of friction, things like that, right? And every scene is slightly different because it's, there's slight variation into how those objects were placed. And so, handling that inherent uncertainty is actually hard. One of the first models, which I wasn't involved in this, but this is sort of one of the first successful models in this, is by some colleagues of mine. They sort of took this, I sort of made this trivial a bit in the beginning, but it's basically what they did is they formulated this as a supervised learning problem. They said, okay, we're just going to predict future frame from current frame, going to make some simplified modeling assumption. Inside this is a recurrent neural network that inside is trying to predict basically shifts of the pixels. So if you're familiar with the flows, it's kind of like flows. And motion flows basically, but learned with a neural network, and that works reasonably well. So these are these are three examples here. These are three examples here. On the left of each is the real sequence of videos. On the right is the prediction. So left is real, right is prediction. Left is real, right is prediction. And you can see that the things just become blurrier into the future, and that's because the model is trained with a mean squared error kind of loss that essentially averages over potential futures, and that's because the model basically makes mostly deterministic predictions about the future. And we had this little data set that we had fun with, this shapes data set, to kind of test this hypothesis. And it's, if ever you're doing research with any kind of video-like data set or anything where there's a bit of stochasticity, it's kind of fun to design your own data set to test your hypothesis. So here in this data set, the task is simple. You're given just one input frame, which is contains the object in the middle position. And there's an actual sort of randomness where the object will just go into some random direction after that. But the model doesn't observe that. It only observes that the object is in the middle, and you're trying to make it predict where the object will go, right? And it can go into 8 different directions, right? So it can go diagonally and left, right, up and down. So there's only one degree of uncertainty in here, the direction. Now, if you train that model that makes deterministic predictions on this data set, what happens is this, right? So you give it, here on the right, basically of each of this figure is what the model predicts, right? So it just averages over all the possible predictions, right? Because it doesn't know, it cannot handle uncertainty. So this is basically your blurriness in effect. Now, this is in some sense, it gives you what it was made to do, right? So the loss function is predict the average over the futures. It gives you the average over the futures, but that's not what you really want, right? When I'm training these models, I don't want the average of all the futures. And maybe here this is somewhat useful because you can sort of deconstruct this average and figure out something. But if you're training this on real videos, the average of all the futures is just a blurry mess. So what you really want is a sample from a plausible future, right? From the probability distribution of all the futures, and that turns out to be much harder. And so we've done a lot of work in terms of introducing some sort of modeling assumptions into these models, or basically modifying them such that we handle uncertainty in a principled way, right? So one of the ways to do this is to use variational methods. variational methods are a relatively elegant way of approaching this. Basically, it allows you to learn a latent representation over a sequence of frames in this case, or videos, that is stochastic in nature, right? So you can sample from this representation. So you can infer, and then you can get a random sample that you can then use to basically guide your predictor to produce a sample that a true sample from your future rather than an average, right? So instead of learning a compact representation that is deterministic, this learns a stochastic representation. And in theory, that should give you, more trajectories that look a bit more like real stuff than and I should have had a slide with the rollouts from this model, but yeah, I forgot about that. But basically, this model does give you more plausible kind of trajectories that do not look like averages over all the possible future states. With the caveat that this, while this works for some kinds of randomness, it obviously doesn't handle all sorts of randomness, right? So it handles things like the little shapes and whatnot, and it gives you better looking videos for robot arms, but it doesn't, of course, doesn't solve the problem completely. Another thing which we did in terms of solving the problem completely, so to say, is we wanted to take advantage of a lot of the computational stuff, computational power that we have at Google, but not only. And we said, can we make these models? It's oversimplifying things a bit, but can we make them basically bigger in some ways? Can we use scale to our benefit, right? A lot of the reality is that if you want to model large sequences of videos, it is probably helpful to have big models that have a lot of parameters. It's implausible to think that we're going to be able to build generative models of videos with tiny compact models. I mean, that would be amazing, but I don't think that can actually happen. So simply because just reality has a lot of variance to it, so encoding it into a small number of parameters is pretty hard. So we took one of these sort of state-of-the-art models from back then, and we said, okay, we need to make it as simple as we can, and just make it in terms of model complexity, and we need to make it in some sort of sense as big as we can. Like and understand, does scale bring us anything useful? And there's a lot of stuff in terms of in this paper, which is I think was a NeurIPS paper. We tried a bunch of things about like removing stochasticity. So can we, is this necessary or not? Turns out to be yes, to be necessary. Can we remove recurrence at all? Recurrence is useful, though you can go pretty far with just a straight convolutional neural network, which is also interesting, right? Like you may think that recurrent neural network is helpful in terms of modeling video because it has a notion of a memory, right? But it turns out that you can go pretty far with just a feed-forward neural network as well, which is exciting. One thing which I didn't touch upon is, okay, we can look at these videos and sort of say, oh, they look blurry, or they look, maybe with little shapes, you can say that they do the right thing or they don't do the right thing. But it's not super obvious how to quantitatively measure the performance of these methods, right? Okay, you have two methods. You ask them to predict the future, and especially if they're both stochastic in nature, how do you evaluate that one future is better or worse than the other future, right? If they're both plausible, how do you even measure if they're plausible in a way that doesn't involve a human? And this is all like, it's a whole area of research. There's a couple of these metrics which are sort of human in the loop, like the Fréchet video distance. If you're familiar with the GAN literature, this is it's the equivalent of the Inception sort of score, basically, but for videos. And there's a lot of more computer vision-y kind of PSNR, SSIM, various kinds of metrics. But if you're doing work in this space, there's always like 5 different metrics that you're trying to calculate, and they're not necessarily compatible with each other in terms of they don't always give you the same answer. So it's tough. There's not like one single score, like classification error or mean average precision for object detection. And most of the times you do have to look at the actual videos and see, oh yeah, I think this model looks better. Oh yeah, this model is trying to cheat by sort of ignoring, especially for robot arms kind of data sets. A lot of the times these models will predict futures that are believable in terms of they look good, but they don't, but they cheat by basically modeling only the arm moving around and not modeling any interactions with the objects, because those are hard. So it's easy to model an arm who's, for which you've seen like tens of thousands of examples. So you can model that with very high precision, but the actual interaction of the arm with the object is very hard. Anyways, back to this model. The biggest model that we've tried has almost 1 billion parameters, and we started with like 30 million, the baseline before that. And the goal of this, as I said, was to get good video results, and we do get good video quality, and as there's this graph in here, and here lower means better, and there's the number of parameters on the x-axis, and so you can see also the videos sort of give you a bit of a flavor as to what kind of videos we work with. So this here is a data set called Humans 3.6 million. This is a data set where it's from a fixed camera viewpoint. Some human is doing something, either sitting on a chair or like moving around. And ground truth is this. You can see, and the left is the smallest model, and in the middle is the biggest model. You see that the smallest model just makes the human disappear. Again, I mean, I'm not saying it's a believable thing, but it's a way for the model to kind of cheat. Here in the middle, there's a robot arm picking a towel. You can see here how the smallest model sort of tries to avoid kind of interaction with the objects. This one is the most challenging data set. Honestly, I was surprised that we got anything out of it. That, most of the time we got something that looks like an artsy picture. But this is basically a self-driving kind of car data set, right? So this is a frontal viewpoint of a car just going through the streets. And of course, this is very hard, right? That like literally anything can happen in this scene. So again, this is more for fun that we did it, but this to sort of give you a flavor of the challenges of this, right? How can you even possibly do a good job here? It's pretty hard. And you can see how we got to 128 by 128. Then this by throwing a lot of resources in. This is very slow to generate. I think this is still, it's a bit, this is about a year old. I think this is roughly the state of the art in this particular field in terms of the quality of the images and the scores that you get on the various metrics. It's obviously not that good. Like if you look closely, you'll see that it makes mistakes. But the problem that we have right now is that we can't really seem to make it much better. Like just throwing more resources at it, like making it bigger, it has a lot of diminishing returns, right? If you make this model, we tried making it like 10 times bigger, it gave us basically nothing in terms of benefit, right? So there's fundamental changes to sort of the inductive bias that we need to make. for things to work better. We tried different other things. And one of the things which we always do is we look at what works well for images, and we try to make it work for videos. There was this fun paper from OpenAI called Glow. This is a class of models called normalizing flows. These are basically probabilistic models for modeling data. But one of the things which they're interesting from the point of view from which they're interesting is that you can do relatively fast inference. So you don't need to do fancy MCMC or anything like that. And you can kind of in parallel generate the latent states very quickly. And you can optimize the tractable likelihood, which is, I think, it's a very special kind of class of models. And we adapted these models for videos. So a lot of people like optimizing or maximizing likelihood because they feel that this is that objective makes sense, right? Maximizing likelihood makes a lot of people that are in machine learning feel better, as opposed to doing something else. And I can totally see that that point of view. We can have a sort of a debate as to whether for video generation, maximizing likelihood is the right thing to do. But if you believe in likelihood, certainly maximizing it is the good thing to do. The other models that I presented, or most of the other models, do not maximize anything remotely related to likelihood. They do something else. You can still sort of try to compute the likelihood of your data under those models. It's a bit weird, but anyways, the point of this is that this kind of model allows you to do that. It gets you some value of bits per pixel, and the model has an interesting latent structure that allows you to do interpolations with it. So you can say, oh, I have this image, like let's call it this like frame number 1, and this image frame number n, and then you can make it sort of interpolate between the two. Right? So go back into the latent space and come back. It's kind of fun. You can do this for real videos. So you can say, here's my first frame, here's my last frame, and this is 2 different kinds of ways of interpolating between them. So if you're looking for models where you can do fancy interpolations, this is definitely one of those kinds of models. It's kind of fun. All right, so I talked a lot about how to do better video generation or prediction, but I haven't one of the ways which I motivated you in the beginning is that we can use them for something useful, right? And Atari is maybe not the most useful application in the world, but many people work on it, and there's a lot of the backbone of modern reinforcement learning research is Atari. Mostly because we can generate a lot of data from it, I guess, and there's a lot of pretty easy to work with, generally speaking. These numbers are a bit stale. Things have improved ever since, but when we started that work, the state of the art on solving Atari was in terms of the number of frames that you need to gather from the simulator in order to train an agent that does well, was miserable in terms of, if you think of this as like solving a real life application, right? That you want it to be solved quick. So like many days or many millions of frames. And sample efficiency is actually important, right? So the number of these frames is, you should try to make them small. Collecting experience in real life can be costly. Robots are expensive, they break. You don't want to have them collect millions of interactions with the world. And we want reinforcement learning to work in kind of scenarios with little experience or even offline. So we tried to formulate this kind of problem of learning in Atari from a video prediction perspective. We're going to think of the sort of action conditional video prediction as a world model. So we're going to try to predict, from these 4 frames, what will the next frame be? Right? And the goal there is to minimize to minimize the number of frames that we need. The precise goal was to do well enough on Atari with 100,000 rewards. So 100,000, I'm not saying that's a very small number, but still much smaller than 8 million. And the main premise of this algorithm is to alternate between learning a model of how the game behaves from existing data. So you collected a bunch of interactions of the agent with the world. That's basically a bunch of videos that you try to split into what you've observed and what ended up happening after you've done something. And you're basically learning a simulator of that simulator, right? And the second part is using this simulator to optimize a policy with model-free RL within the simulated game environment, right? So within this world or simulated world that you've learned, you will learn how to solve the task of beating the game. This will make your agent a bit better. You will use that agent to collect more data. So it's kind of a circle like this. I think we did like 10 iterations of this, where we collect data, train the agent, evaluate the agent, which implicitly collects data, and so on and so on. This model is much, much simpler than the humongous $1 billion, no, maybe not dollar, parameter model that we had, because it would be just completely impractical, right? So one of the realities of trying to use these video models in real applications like Atari is that you need to sort of scale down your expectations by quite a bit. You cannot use a 1 billion parameter model in the loop while doing RL. It would just take like years. I think we would have started in 2018 and would have finished by this talk now. So like even with this kind of relatively tiny model, I think our experiments took about a week. And this is truly a very compact model, in relatively speaking. It has a bit of a latent VAE thing happening here that learns a discrete representation for stochasticity. But otherwise, it's almost all convolutional kind of model with skip connections, basically, with a deconvolution tower at the end for prediction. I'll show you a couple of videos. This is just basically the model predicting, just rolling out into the future. And I don't know if I have more, not here, but oh yeah, this one has actually comparisons between prediction and ground truth, right? And then here it's supposed to be the difference. So on the right side, it's supposed to be the difference between the prediction and the ground truth. So you can see it can simulate the simulator pretty well. I like this one because this one is good. So this one is the prediction on the left. This one is the ground truth. And this is the difference between the two. And one thing which can go wrong here is that in the prediction, it can miss the tiny, but the most important bit, basically. So here it misses the bullet from this tank, right? And the point of it's a shooting game, right? So like, I think this is one of the problems that we have a project right now about this, is how do you have these models sort of focus on the right thing rather than sort of modeling random garbage in the scene, but totally missing the thing that matters. I don't want to say the most, but one of the most important things in the scene. And this is a bit sort of tricky to explain here, but generally on these, if you're not familiar with the Atari benchmark, there's like, I don't know, 50 something games. Each game is a bit different. And they have different levels of, how complicated they are to solve. And it also depends on like how many, again, the sample complexity is an important metric to consider. So what we looked at, the red line is basically, how many steps our agent takes, which is 100,000. And the blue is how many steps does it take for the state-of-the-art agent, either PPO or Rainbow. Those are model-free agents, those that do not have a world model inside them. How many steps it takes them to get to the same score as us, right? So for Freeway, you can see that it takes the state-of-the-art agent takes 10 times as many samples to get to the same score as us. You can see for the majority of the games that we looked at, our models gets to the same score faster than the model-free agents. I will say that with a caveat that if you run those agents long enough, the state-of-the-art agents, the model-free ones, they will get to a better score. And whereas the models that we looked at never tend to, on average, they at convergence, we don't seem to be able to get to the same kind of score. It's not far, but there's a small but non-trivial difference between the two. So it's unclear why that is the case, right? And that's a pretty common theme in a bunch of these approaches. They get to a good enough agent quickly, but they can't seem to, if you give them truly sufficient amount of data, they don't seem to get to as good of an agent as if you were to just disregard the dynamics of the world. And we haven't done that yet, but it'd be good to apply this approach to other domains other than Atari. The main problem there is that Atari, as simple as it is already pretty complicated for us to run. It was already pretty slow. So anything more complicated than that would have been even slower. And as I already sort of hinted to before, how do we predict the important things is pretty hard, right? And I'll give you some sort of failure cases, which are fun. we call this the ghost. Somehow in Pong, just started doing this. And if you don't know the boxing game, there's only two usually game players, but somehow this model invented a third one here, which is a bit unfair, I think, for the black one. But yeah. So there's a lot of, this is, like clearly this has never happened, right, in the training data. So somehow this has happened in the predictions, though. This is sort of parallel work to ours, and some of these people they've ever since they worked with us as well. This is Planet and Dreamer and a couple of other sort of state-of-the-art approaches that do the same, have the same idea as us in terms of predicting the future or learning the dynamics of the world, but instead of predicting directly in pixel space, they try to infer some sort of latent representation of these pixels, of these videos, and kind of do the prediction in that space. So roll forward in the latent representation rather than in the pixel representation, and that can be better in many ways. In that, this is conceptually simpler and whatnot. It's not super obvious. One good thing about predicting pixel space is that the pixels give you the one ground truth, right? That that happened. There's no ground truth for your hidden representations. You don't know what should have been the right hidden representation for that particular future. But maybe it's a nitpick. So we've also done, I see that we're running out of time, but I will just quickly say that we've also tried to explore the long horizon problem. And the horizon problem is pretty tricky because, as I said in the beginning, the longer you try to predict into the future, the more diffuse and the worse basically your predictions are. And we've tried to decompose the prediction problem into two subproblems: one that predicts kind of intermediate milestones for an agent, and another where you have like a low-level controller that tries to predict how to get to to the intermediate milestone from wherever you are. And it works for a couple of these maze problems, but we haven't yet tested it on anything sort of more intricate than that. I will make a quick plug for a playground that we just released. And I'll say that, generally a researcher in this field has a new idea for either a model or an environment or some planning mechanism, maybe doesn't have the infrastructure or the know-how to try the whole pipeline, this whole like pipeline here. And so we wanted to enable this use case of kind of bring your own piece of the puzzle. And so the solution that we came up with is this kind of lightweight platform agnostic API or library. And the goal is to kind of have this simple interface that enables the researcher to use it within kind of a day-ish. There's a few high-level methods, but generally there's a lot of stuff that's implemented for you under the hood, and it implements this training loop here. And we put up this on archive. I think there's a blog post or something. That we put this basically code base that allows us for comparison of the methods on equal footing, right? So we try to answer a bunch of these questions of like, is predicting images useful, or is it better to predict latents? How important is to predict what the reward will be in the future? How important is it to model the dynamics in latent space versus observation space, right? Is it important basically to model how the images change from time t to t+1, or how the latents change from time t to t+1? And a couple of the findings that we have is that the more pixels you predict, the better the agent becomes. It's kind of maybe obvious in retrospect, but it wasn't so obvious when we started. There's a very strong correlation between image prediction accuracy and task performance. So the better you are at predicting what the future will be, the better you will be at performing that task. But not so strong correlation between reward prediction and performance. So just because you know how well you will do at something doesn't mean that you will do well. In other words, you can always imagine this, that if you have a very bad agent that is very good at predicting that it's bad, well, it will obviously not do well, right? So just because you have a very good reward predictor doesn't mean that you'll have solved the problem, right? So a lot of people sort of seem to confuse those two. Anyways, so I'll summarize quickly that despite amazing progress and hype, computer vision is not really solved. I don't know. Some people have claimed this, especially popular press. There's many things in computer vision that have not been solved. Anything that deviates from basic classification or object detection template with lots of data and all that stuff is kind of hard. If we try to do more ambitious things, we should be building these predictive agents that can learn from self-supervised interactions with the world. Building these unsupervised representations of environments is an open problem. We don't know really how to deal with uncertainty. We know, I think, even less on how to do efficient planning. Like, even if I give you a model that can do all these rollouts into the future, how do you choose which of these futures is closer to your goal? It's pretty hard. Current projects that we have, we want to understand the role of learning a model for various of these things which I motivated in the beginning: generalization, zero-shot learning, domain adaptation. So we don't care just about end performance. Like, we don't just care about the model that can like grab a mug, right? I want a robot to be able to grab any mug that it finds, right? Even if I just describe it in words without any examples of ever successfully grabbing in a mug in a place that it has never been at, right? So things like that. Yep, thanks. The library is there. That if you just search for Google World Models, probably will find it. One day we'll put a bunch of these collector trajectories. There's something about legal clearance that makes this hard for some reason, but we'll get there. The current focus is we try to scale our work beyond DeepMind Control Suite, and the long-term goal is the same. We want to understand how to create these sample-efficient agents that can bootstrap themselves and with little expert data can solve multiple tasks at the same time in visually complex, not like Atari and not like the DeepMind Control Suite, diverse environments. And many thanks to a bunch of my colleagues who are on these papers. and who have done a lot of the work. And you can always, reach me at my first name, Dumitru@google.com. Thank you. I think that's it.